So the etching step is very critical. That's very critical to box micromachining. Because our silicon box thick. How to control the thickness is very important. So several ways, I summarize here. My way, big group etching. In the optical inspection, somebody used the optical interference method. Directly see the membrane and try to find out what the thickness is. And P plus etching step, we are talking about PN junction, reverse bias etching step, right? And also another method I have not mentioned very precisely. Actually not the anisotropy etching, it's the isotropy etching. So the reason why I have not mentioned that. But anyway, if you compare all these methods together, you can see whether it can be batch process, non-contamination silicon, in situ monitoring. In situ means that we do the measurement at the same place and at the same time, right? In situ. Ever heard that? You ever read that, right? At the same time, at the first moment, in the right place, doing the measurement. And the measurement range, what's the range you can measure? And resolution, resolution is also very important. Can you as small as possible, right? Over very coarse. So we summarize globally, you will see optical method is good. Optical method is good, but only for the very thin layer, almost transparent. You can use the thick optical method to optical interference method to judge the thickness. But for the thick, maybe have some difficulty. Anyway, our method is very cheap and very easy, and also has resolution we can accept. Compared to optical, maybe nothing. Optical gets 0.1 micron resolution. My way is only 1 resolution, 1 micron. But 1 micron is very open in the spec of with silicon wave. It's quite good enough. It's good enough. Especially for our mechanical field. For our resolution, always 10 micron, right? For us to do the machine shop experiment, right? Less or minor machine, right? The machine only can your resolution about 10 micron. But right now, micro machining and less, you decrease to 1 micron. It's much better than our conventional micro machining way. Now you can see other B plus, you have the contamination method drawback and measure actively. You cannot do the measure in real time. PN junction also has the problem. No measure on the real time. So you can compare the performance and to select what you want. So this is our methodology here. There's a comparison to etching stock method. So for silicon box micromachining, you always need to think about etching stock. Okay, so I need to go to another way we make it about the silicon anisotropy etching. It's 110 silicon. 100 silicon we are familiar with the V shape, V group, right? But sometimes I want to do the vertical etch. Vertical etch. Vertical etch, you need to select another kind of silicon wafer called the 110. 110 wafer. You need to order, special order from the company. Say, I need 110. If they provide you 110 silicon wafer, you can find an orientation of your wafer can make vertical etching. So this geometry is very similar to our cooling film, right? Cooling film. Very similar to our cooling film, right? We call it you can say cooling film. Very similar to the cooling film. So this cooling film can use to micro heat exchangers. You can use the micro heat exchanger. The heat transfer coefficient will be very strong. Number 2, you can apply this technique to the high aspect ratio micro cantilevers for the astrometer. This is a parameter. we have not mentioned about the sensor and actuator. The sensor actuator is another course for the computer science this time. But if you need my teaching material, I can give you, no problem. I mentioned here, in the spectrometer, we need a mass and a spring. Mass spring, they can do the vibration according to the acceleration from outside. Vibration. And this film, why can it vibrate? Because we have the very flexible and very thin, sensible the vibration be very, very nano. Very, very nano. So how to make it very nano and narrow and what? Tall. We call the high acceleration. High acceleration means that the height divided by the width. The ratio may be larger than 10 or even more. And this kind of structure is easier for you, for this vibration mass, to do the horizontal vibration. So it's a vertical edge. This is a kind of vertical edge. So this kind of edge or this kind of edge, depending on the 110 silicon anisotropy etching. But the problem is you need to align very good. Align the wafer. Wafer line alignment is very, very important. You need to align to its primary frame, very, very perfect. And in ordinary, we have with the error about 1 to 2 degrees. 1 to 2 degrees means that we have some deviation of the real crystal orientation. So you need to identify your orientation. So this plot is only showing you how to find the exact primary frame. The primary frame we see from the wafer is not exactly the same as the exact direction, the primary frame direction. So you need to do more etching, one more etching on this. We use a lot of faint lines, long streak, and try to calibrate which direction is right. If the direction is right, then that long thing will be preserved. So, for example, this is the right direction. Other faint line direction are not true. So use this kind of method, you can find the exact direction of the single crystal orientation. And based on this line, it's our new primary frame. We use that to align our this contour, the mask contour, then line to then calibrate primary frame. Try to reduce the error. You say 1 degree is nothing, right? Not true. 1 degree is very big. 1 degree is very big. 1 degree is equal to about 2%. 2% radian. About 2% radian. 2% radian, it means that if you have a long bar, 1 degree error. It's very easy for you to do it. If your bar is too longer, all of the bar will be undercut. Because you can either undercut by this way, and the fiber disappear. So the alignment should be very, very accurate. I have not mentioned the alignment error about this anisotropy very precise. But here I only show something. You need to identify the real primary frame. The primary frame provided by the wafer is not true. It's not true. So you should find it by yourself. And based on this new primary frame, you can do the long bar etching. Otherwise, long bar etching will be fail because the undercut is very much. I can crop more here. For example, if we had this long bar should be preserved, but our wafer actually had misalignment angle like this. So you can see. So we hope this will be reserved. But due to the direction, is real direction like this. So most of the material will be undercut. So is the reason why we need to do the very precise alignment. So we have some protest the key. We test the key. Bend line outside bending. So the rest to the left, only one is the real primary. Roughly, I think I want to talk about it because on the recipe, try to maximize, optimize your recipe. Try to reduce the roughness value as small as possible. Basically, the etching rate about the tail edge of the silicon getting less. You increase the concentration. Yesterday I mentioned increase the concentration, the etching rate go down. Roughness also getting better. So sometimes we try to increase the concentration somewhat. Don't let the concentration too low for our roughness. Roughness is also very important for our machine device. Okay, so cable edge etching about the silicon we have finished. The next one is talking about the hydroglass. Hydroglass is the protection medium, protection material for your silicon. Silicon we have the very fragile, maybe we have very fragile membrane, thin film, right? Can never be very easy to be broken. So we need another cap to protect it. So glass is our protection cap. We try to protect inside. But how to protect? You need to do the bonding. You need to bind your silicon frame with the glass. So you need a glass, you need a hydroglass. Hydroglass, we do some matching in the lens is just for matching the geometry for the silicon. But sometimes we need etch, a groove. Sometimes we need to penetrate it. Groove is very easy. Groove is wet etching by BOE. HF. We use the HF to do the etching on the glass. If you want to drill the hole on the glass, we use electronic arc discharging machining. Arc discharging machining. Actually, also very easy. You can do it here. Very easy. You have the KLG solution. The glass here. You want to penetrate the hole. I want to penetrate this hole. We use the needle, ordinary sewing needle is fine. Ordinary sewing needle is fine. And connect to the high voltage. Connect to the high voltage power supply. You need about several hundred volts, high voltage. And you have the electron. Electron can be preserved in the tail edge. And then you don't need to do the pattern very specific. You can find some easier also find. When you apply the voltage here, you can start to erosion. There's a very strong erosion about here. So about take you several minutes, 2 minutes, 3 minutes. You can machine a hole like this. So whatever etching a groove or etching hole and the hydroglass is no problem. Then we need to do the anodic bonding. Anodic bonding is trying to bond silicon and the hydroglass glass together. Bonding. After bonding, your overall structural strength is very strong. You will protect the very sensitive vibration part will be preserved. How to make it? This is also our homemade anodic bonder. You can go outside and buy a machine of anodic bonding. Maybe cost you about several times, maybe 60 less or even more. Very expensive. But you can assemble. This is our self-assemble anodic bonding made by designed by umachining. It's a power supply, 1,000 volt power supply. It's an IR heater. IR heater can increase the temperature about 600 degrees C. 600 degrees C. The IR heater. And above this hot plate, this heater, we have our silicon on the bottom, glass at the top. And you apply the negative charge on the glass, positive charge on the silicon, and then you do the bonding. Very easy. You don't even need not do the processing in clean room. Ordinary press, fine, successful. So it's very easy to make. It's called anodic bonding. You can bond your silicon with glass, or even silicon with what? You can use the you can even bond the metal with glass, but you need to polish the surface very well. Polish the surface very well. They have the perfect contact. Perfect contact.
This is because of resistance. Resistance. Resistance.
Resistance. What is it? You mean the glass? Yeah, silicon other yes. Yeah. No. It's a perfect contact. So you need the surface of the glass and surface of silicon. Beautiful polish. Beautiful polish with the roughness. I mean the average roughness should be as small as possible, several nanometers, very smooth. Rough surface you cannot do that. Polish. And anodic bonding, why it can work? We use the electrostatic force to pull these two kinds of surface closer. It's an isolator, right? It's an isolator. So apply electric field. Right? Electric field. Very strong electric field here. So here there is a very strong electrostatic force attracting two faces together. Perfect contact. But when we have the perfect contact, what's the force right now prevail? Van der Waals force. Van der Waals force applied. Ordinary matter I cannot attention, right? I cannot attention because it's too rough. So no Van der Waals force. But you very smooth, polish, sticky. Something like the gecko, right? Gecko on the roof, gecko. Why gecko? Climbing on the roof, no falling down because they use the Van der Waals force to the attraction. Similar to this, we apply electrostatic force. Okay. Very close contact, and after contact, no separation. No separation. But we need to increase temperature. We need to apply voltage. Apply voltage for you to have the perfect contact, pulling by electrostatic force. Heating voltage, heating temperature up to about 400 degrees C or 500 degrees C can induce some sodium ion transport. So finally, the interface will have some, there is some partially oxidation bonding will happen over there. So anyway, so these two conditions will provide high temperature, 500 degrees C, 400 degrees C, high voltage of 800 volt to 1000 volt will be a problem. Even more, you will consider what is that? This stuff is graphite. It's graphite. Graphite is a good material for you to have the electroconductivity and the thermal conductivity at the same time. Because at this moment we need to do the perfect electrical contact, right? And also we need to do what? Heating at the same time, conducting at the same time. So the best candidate for this bottom material is graphite. So we use a break of the graphite here. Conduct here and heating through it. Perfect. So it's not costly. It's about the overall facility over here maybe two less. Two less. You can finish all the facility. That's very easy. So you need to do a kind of metal to glass or silicon to glass. Right? You can do this kind of bonding methodology. It's a bonding. Not only for maps. If you want to do something bonding for you, for example, I remember next time you want to do some cooling, right? Specimen, tensile stress, tensile testing. Tensile testing, you will see the standard specimen, very big, right? And our specimen very small. So how to make the cooling, how to make the tensile test. So maybe you can use this kind of idea, combine your specimen with the standard test specimen. The bonding strength is very strong. The bonding strength we will try to peel it out. After bonding, we use a weight to try to separate. Very hard. We separate. Finally, we found that broken, either glass broken or either silicon broken, but the interface is still fine. So it means the bonding strength and the interface larger than the rack limit, right? The value limit of this kind of material, very, very strong. So it's anodic bonding, very easy to make, but useful. Not only for the memory sensor package, or maybe also useful for other applications. Another way to do the bonding is silicon to silicon bonding, because silicon to glass bonding still have the problem of thermal mismatch. We have the problem of thermal mismatch. Our process temperature should be as low as possible. But due to the requirement of anodic bonding, the process temperature here should be at least 400 degrees C. 400 degrees C bonding, perfect. But cool down to ambient temperature, 25 degrees C, whatever. The shrinkage is different. Shrinkage of glass and the shrinkage of silicon different. For parent glass, it's very strong glass. It will not be broken, but will distort it. Distorting about your specimen is no good actually. Even the inside the structure has some residual stress. Due to the thermal mismatch. Residual. Inside our microstructure. Have this kind of problem. So the better way to do that is the silicon to silicon bonding. Why? If you can do the bonding between this silicon and another silicon, two silicon, same material, same thermal expansions and extraction. So no thermal mismatch, no residual stress. Problem appear. Is it easy to make? I can show you very hard to make. You need class 1 clean room. You need a class 1 clean room to do this kind of bonding, silicon to silicon direct bonding. If we have no clean room, class 1, you cannot do that. Our clean room in Hanggang University was only 1,000. So I have ever tried this, failed. Our particle too much. Okay. Each one spot of the particle with a 0.1 micron will induce an area about 2 centimeters per square fail. So impossible to finish, to complete this kind of process in ordinary clean room. But if a clean room is good enough, you can do that. For example, in TSMC, all of them have good clean room. They can do that. Very easy. Just two kinds of silicon wafer with a hydrophilic treatment. Hydrophilic treatment, I said yesterday, we just dip into the prana solution, sulfur acid and peroxide, right? And peroxide together. You can change the surface into hydrophilic. Hydrophilic is something like this. It's a hydrophilic surface. Water, very easy to do the weighting about the surface. dry it. You can do the drying of the surface and put this silicon just direct contact and just push in the clean room. Push it. You can bind. You can bind. But at that moment, just temporary binding due to the hydrogen bond. We talk about that. Hydrogen bond. It's a hydrogen bond. Two kinds of secondary bonding force. One is van der Waals force. Another one is hydrogen bond. It's a hydrogen bond. The bond strength is not very good. It's not very good. So it should be enhanced by anneal process. It means that you increase temperature up to about 1000 degrees C and gradually down. Then you can enhance. You can transfer the hydrogen bond area into very perfect covalent bond area. Covalent bond area. And we will call it a dehydration process. Dehydration process. And even you increase the temperature very high to 1000 degrees C, no problem about the thermal displacement because both material same, silicon to silicon, perfect. No problem. So it's a very good direct bonding method, but not. You can only process in a very clean space. This is one limitation. Finally, there is another method called the gas phase silicon etching. In the formal introduction about the micromachining, we use the KO etch, right? And atomic etching solution to do that. So we can only make the rectangular or pyramid shape B group, U group. Not very, you cannot arbitrarily design your contour. Your photo mask pattern always rectangular pits, rectangular B group. If you change to 110 wafer, vertical group, okay, that's all. But you cannot do the circle, for example. Circle, impossible. You cannot do the circle pattern, vertical edge inside, impossible. Not impossible. So in recent years, there is an expensive equipment called the inductive copper plasma etcher appeared. Very good dry etching machine. This kind of dry etching machine can provide you a post process. This kind of post process can do etch protection, like we drill and compound. So you can penetrate your silicon wafer, but the hole diameter very small. For example, your hole diameter may be only 50 micron, but you can drill through the 500 micron thick silicon wafer. Aspiration can be as high as 10, no problem. But it is a ICP, dip, or sometimes we call it a dip, RIE. ICP equal to this term, dip, RIE, dip, RIE, reactive ion etch. Of course, this machine is a little bit costly. One piece about 1 point, 2 point. You mean bonding? You mean under bonding? Yeah. It's visible here.
By using this 2 metals, let us take modern physics.
Oh, you must have one material is insulator. If two thin, if two conductor, then there is no voltage difference. You cannot generate high electrical field. No high electrical field, no electrostatic force for you to the perfect contact. So you must have one material is insulator. Ceramic, glass, and so on. give one metal to another one metal. You can use other way, for example, diffuse pump. Just try to increase the temperature and compress it, try to do the diffuse pump.
What do you have?
Reversible doesn't work. Because we have already tried. If you reverse the polarity, right, positive or negative side, you will see there is no more. This interface will be no more the anodic, it will be cathodic. If cathodic, the interface, temporary contact, but not perfect contact. It means that you will have some partial force. If intrinsically there's some partial force, there's no advantage to the excited. If you cannot infuse the iron in the proper direction, so finally you will feel some rocking powder inside this interface, no bonding.
We have later bond between the atoms. If you want to take the bond, you want to break the bond. If the polarity is
No. It's not a reversible process. It's an irreversible process. Yeah, you bound it and then you cannot detach anymore. You cannot detach. It's not a matter about magnetism. It's not a magnetism. It's not even to say electrical magnet. It's like different. Every bonding, it just one force bonding good and no separation. You know, for some optical element used in some laser measurement, they have some splitter. Have you ever used the optical element lens, or some optical set, they use the splitter. Splitter the block can separate one light into two branches of light. The splitter, how they use two prisms. They use two prisms bonded together, two prism glass bonded together, how to make them. They use the single way, but they only they don't use not in bonding. They try to polish the glass surface very perfect into nanoscale roughness and contact in a very clean environment without any glue. The perfect contact, no separation anymore. So, about your question about you want to do two kinds of metal, try to do the bonding. One possible way, very simple, that maybe you can use if you have very local, clean environment, right? You make the metal surface contact together, maybe hopefully you can do the bonding. But the environment should be very clean. For example, you maybe need a vacuum environment, and the surface is very, very, very fine. You must measure the surface roughness as small as nanometer. RA, and you should be as small as nanometer. And two different kinds of metal, maybe in contact. Depends. Okay. Sometimes, if you want to do the diffuse, you can only contact it for very one force to use. You don't need to hit it. But if you want to do the diffuse, right? You similar for the interface. I hope there is an alloy exchange, right? For example, we have gold and we have copper. We try to diffuse each other. Yeah. So you need it. Then you can have some for the diffusion pump. So you have gold interface layer and the copper. The interface layer is alloy. Perfect. So you can looking for the term of diffusion pump. Yeah. Someone has never done that.
The existing, in this case, the
Don't use the cross. You don't need to use the cross. Vacuum is only one to provide you a clean environment.
Using this method, is it possible? Using the bonding.
We want to package our sensor in a wonderful way. For example, there is the center part, we have vibration and inside. If we cannot cover it, seal it, very easy to be broken by altered rifles. So we want to package it. We use this kind of metal to protect and bond and package our sensors. So ICP is good, but ICP is also very expensive, not feasible here. So another way also, so this section actually just for your briefly understanding. This world has some other kind of machine available to doing the very special etching. So ICP can do the vertical etching very good. Gas phase, silicon phase, etching, two kinds of gas. One kind is sodium dichloride, another one is bromine trichloride. If you know the chemical, you know both of the gases are toxic. Toxic gas because the chlorine, right? Chlorine is a very reactive gas, and you are compound with the inner gas, sodium and bromine. Bromine is also the toxic. So these gases are toxic, and they should be preserved in a special reactor to touch with silicon. Whenever they touch with silicon, reaction happens, etching happens. So it's a very special equipment for doing the etching about the silicon. But their function very limited to some specific function about the anti-stiction we are introducing the surface micromachining. Okay, so maybe when we talk about the anti-stiction, and we mention this once again. I will mention this once again. So it's nothing like this. The bromine trichloride. This facility is in the Caltech. The facility is in Caltech, California Institute of Technology. The facility is very wonderful. So, but there is some because this kind of gas is very toxic. So there is some poison toxic gas detection system. If any problem about the leakage, you're alone, and the people inside the clean room get away, go away right away, get out right away, and someone have the mask and all kinds of space, like an astronaut. They will have the facility go inside for inspection and repair the system. So costly, very costly. So the function for this kind of bromine trichloride etching. I think I will mention this after we talk about the surface micromachine. Okay, so next topic is surface micromachine. I just pray I have no time today. Maybe we still have 10 minutes about this. So I only mentioned some parts about the surface micromachine. So right now, have any question about the bulk micromachining? Bulk micromachining. Bulk micromachining, you can do that if you are okay. For example, etching, right? And anisotropic etching is easy. And anodic bonding also easy. It's easy. It's easy to make. And regarding some, I believe in your lab,